Good evening, everyone. Welcome to the tutorial session for circuit analysis for analog designers, week one. So we will be discussing some problems based on the week one's material. So first of all, let's quickly. First of all, hello. Yeah. First of all, let's quickly take a look at what all has been covered in the week one's material. So the first thing was the incidence matrix. So we covered the incidence matrix first, the concepts of graphs. So let's say we have a skeleton of a circuit with four nodes, and we know the currents I1, I2, I3, I4, I5, and I6. So we have a number of nodes equal to 4, number of branches equal to 6. So we can make an incidence matrix of dimensions n cross branches. This is the augmented incidence matrix, and if we if we put the fourth node to ground, so this is the AUGA. I'm calling this augmented incidence matrix. If we consider one node as ground, and then we get the actual incidence matrix, that is of n minus 1 cross B. So now what we need to look at is, so so we if we consider the matrix E with all the branch voltages, and we consider the vector I with all the branch currents, and we have the vector V with all the node voltages. So in form of the incidence matrix, we can write KCL as A times I equal to 0. We can write KVL as we can write KVL as so KVL will be V times A transpose equal to E. So V is considering all the node voltages, that will be n minus 1 cross 1. I will be B cross 1, and similarly E will also be B cross 1. So from here, mm, sorry, this is written ulta. So we have A transpose times V is equal to E. So this is how we denote KCL and KVL. Then we learned about the Teligans theorem, and from Teligans theorem we derived reciprocity, and then we derived interreciprocity. So now we learned that this interreciprocity can be used to find noise transfer functions. So in this tutorial, we will take examples of some standard circuits that are regularly used in analog IC design, and we will try to apply inter-reciprocity theorem on those circuits. So let's start with that. So the first circuit, we consider this one. So this is uh, a low pass filter that is made through two op amps, and so consider this circuit. So it is basically a low pass filter that is made through two op amps, and you apply input at the node 1, and you get output at node O. So we will try to analyze the current from the noise transfer function. What we'll do, we'll analyze the noise transfer functions from each of these resistors to the output. So first of all, we will see how the whether the reciprocity works on this or not. So uh, now this circuit has active components. So what all active components the circuit has? There are two op amps and one voltage controlled voltage source. So this is the voltage controlled voltage source. So due to the active components, we will have to use the inter-reciprocity theorem and not the reciprocity theorem on this network. So inter-reciprocity theorem, we have learned the following things. So first of all, let's have a quick view on how we write the inter-reciprocal network. So this is a chart that one can follow. So these are the transformations of controlled sources. So what basically we have if we have a voltage controlled voltage source that will transform into a current controlled current source. So basically we need to make sure that the skeleton of the transformed network remains the same. So we can see in case of the actual network, we have an open circuit on node A and a short circuit on node B. A short circuit because the impedance of a voltage source is zero. So, and similar thing we have in the transformed network. We have open circuit because this is a current source, open circuit on node A, and a short circuit on node B. So, and how do we decide the sign of the network that is that is coming after transform? So let's say I try to increase this voltage. If I try to increase this voltage will also go up because we have a positive voltage controlled voltage source. So the same thing should happen here in the opposite in the transform thing also. Let's say if I try to increase this voltage, if this voltage is increased, so the amount of current that tends to flow in this branch will also increase. And if the amount of current that tends to flow in this branch will increase, this current will increase. And this current, if pushed into this node, it will tend to increase the voltage of this node. So that's how you need to decide the direction, the signs of all the control sources. And once you have decided it, you can once you know this, you can use them to find reciprocal networks, inter-reciprocal networks. So other thing is So this is basically transformation of controlled sources. Now let's see what we do in case of op amps. So inter reciprocity with op amps. So what are op amps? So op amps are basically op amps is basically a controlled source. So or better I should say interreciprocity with op amps in negative feedback. So op amps are kind of so the one thing they are a controlled source. Other thing they have very high gain. Okay, so let's consider any kind of current source that has say a controlling terminal. So this is a controlling terminal. Let's call this in, and this is a output terminal, control terminal. Let's call this out. And somehow we have a negative feedback from the controlling terminal to the from the output to the controlling terminal, and this gain of this thing is tending to infinity. So in this case what will happen is, since the circuit is in negative feedback, so the circuit is trying to be stable, and none of the node voltages or branch current can go to extremely high values. And since this gain is very high, so and the output of any output node of any negative feedback in the circuit will have some finite value. So this value will be something finite. Now any finite voltage or current when divided by an infinite gain, the input terminal will have a quantity that is zero. So what the bottom line is that if an op amp with a very high gain is connected in a negative feedback, the controlling terminal of that op amp will go to zero. The controlling quantity of that op amp will go to zero. So if we consider if we go to this chart again, so an op amp with a very high gain in negative feedback can be considered as any of the circuits. It can be a VCCS, it can be a current controlled voltage source, it can be a voltage controlled current source, or anything. Just that its gain has to be infinite. For example, if the gain of this thing is very high, so we will have virtual ground at this node and this node, and VA will be zero, so that it can have a finite output over here. Similarly, in this case also, now let's consider when the controlling terminals are controlling terminals are current. So there is current input. In current input also, since this output voltage or output current has to be this value has to be this value has to be finite. So again, the input currents will be zero. Now, due to the short circuit, the virtual ground is already there, as this voltage and this voltage will be same. And on top of it, since this IA is tending to zero, so you get a high impedance node over here as well. So this means to say op amps can be modeled by any of the current sources depending on what kind of circuit. So depending on the what is convenient. So in this circuit, what we just can do is, while making the inverting of this, we will just make op amp like this. So this will make sure that in the reciprocal network also op amp is in negative terminal, and we'll just change the direction of this op amp, and we'll get the inter reciprocal circuit. So let's copy the circuit to a fresh page and analyze this circuit. So first of all, before we start analyzing it with inter-reciprocal theorem, to show that the inter-reciprocal will do, we will first write the transfer function from input to output in a conventional way, and then we will proceed with the inter-reciprocal theorem. So for the conventional thing, let's call, so this current that will be flowing is, so here I will write conventional method. So this current flowing is V in by R. That current and this voltage over here is V naught. So this current that will be flowing is, let's say, uh, V. So okay, so let's skip the conventional part for now. So what we will just say is, I will directly write the conventional, the transfer function from input to output. You guys can do the math for the conventional part. So if we write the transfer function from input to output, this is what we get. V out by V in is equal to 1 upon S square by omega naught square plus S by omega naught cube plus 1. Now this is a standard second order biquad. So and the terms omega naught is equal to 1 upon RC, and the Q comes from this resistor. This is the resistor that controls the quality factor. So from there you get the Q. So we can write this as 1 upon D of S for future references. So just keep in mind that the transfer function from input to output is a second order all pole transfer function, and we are calling its denominator as D of S, which has a central frequency of omega naught, that is 1 upon RC, and a quality factor of Q. So now let's try to apply inter-reciprocity theorem on this network. So we'll again go to the next page. So we will apply the inter-reciprocity on this network. So how will we do that? We will short the de-energize the input voltage source, and we will invert the op amps. Same thing we will do for the voltage controlled voltage source also. So voltage controlled voltage source will transform into a current controlled current source. So now let's see how we will transform it. So again, this is the one that we need to transform. So if we increase this voltage will reduce. So now we are to put a current, so a current sensing over here. Let's call this I naught, and what will be the direction of the current source that we have over here. Let's try to find it out. So if we try to increase this voltage, this I naught will increase. Now what we want is that in that case, this voltage should reduce, as the relation previously we saw is the opposite. Now to reduce the voltage as this node, this current source should tend to pull the current out of this node. Hence, the direction will be this thing. And since the gain was 1, so here also we keep the gain as 1. So this is what we have as our inter-reciprocal network. And to find the transfer function of noise from all the resistive passive sources. So these are the sources. These four resistors over here are the sources of the noise. So to find it, what we need to do is find these currents. Let's call this as I1. So what we'll do over here is so we will inject a current at the previously known output terminal. Let's call this I in, and these currents let's call as I1, I2, I3, and I4. So we'll try to find all the currents one by one and see what we get. So we have this, the total current that is going in this direction is I in minus I naught. The same current flows through both the parallel combination of QR and C, and the current at so the voltage at this output node can be written as follows. So how can we? So this voltage over here, let's call it Vx. Vx is equal to, since this voltage is short, so this voltage V is equal to 0, and the voltage at the output of op amp A1 is Vx, and we can write it as 0 minus I in minus I naught times this impedance. This impedance, let us call it Z. And what is Z? Z is basically a parallel combination of QR and capacitance. So that is QR upon 1 plus SCQR. So let's call this equation as 1. Now what is I3? So again, this node is 0. So I3 is basically Vx minus 0 by the resistance R. So we can write it as minus I in minus I naught times Q. So this R and this R will be, so this R and this resistance will get removed. So I in minus I naught by Q divided by 1 plus SCQ times R. So we have one more equation. Let's call this as equation 2. Now this I3, since it can't go here, so all this I3 will flow through this capacitor C. So the voltage at this node, let's call Vy. Vy will be minus of 1 by SC times I3, and that comes out to be minus I in minus I naught into Q divided by 1 plus SC R times Q into SC. Now, if we try to manipulate this equation a little bit, what we get is minus I in minus I naught divided by SC by Q plus SCR, S square C square R. This is the voltage at node Y. Now, if this voltage Vy is known, so the current I1 is basically Vy by R, and similarly the current I2 also is equal to Vy by R, and I2 is basically minus Vy by R, and I0 is equal to Vy by R, because I2 is nothing but negative direction of I0. So we get this from here. So I1 equal to I0 is equal to minus, Vy by R, and Vy by R is nothing but just a minute. So here, since I3 already has a negative sign, so here we will have a positive sign. So Vy will be plus I in minus I0 divided by SCQ plus S square C square R. So please keep in mind that thing. So Vy by R comes out to be V in I in minus I0 divided by SCR by Q plus S square C square R square. And now we can just take this term and equate them. So what we get from here is I0 1 plus 1 by SCR by Q plus S square C square R squared equal to I in divided by SCR by Q plus S square C square R square. So if we manipulate this, we get the following thing. By Q plus So as we mentioned in the starting, so if we compare and this I0 by I in is nothing but equal to V0 by V in, where V in was the voltage at this node and V0 was the voltage at the output node. So from here, this is equal to V0 by V in, and initially as we wrote the transfer function, let's bring that transfer function to compare it with the derived transfer function. So if we keep the transfer function side by side, so we can see that we have omega naught equal to 1 by RC, and if we have this, we get the same transfer function as we mentioned before. So let's call this 1 by D of S. So now what we have is, so I0 by I in we have found as equal to 1 by D of S, and this is same as I1 by I in, and this is same as minus I2 by I in, where I'll copy this image on that page also. So I naught by I in we found as 1 by d of s, and since this is Vy, so this was nothing but equal to Vy by R. So Vy by R is so I naught by In and I1 by In are the same quantities, that is Vy by R, and since I2 is in the reverse direction, so 1 by d of s is minus of I2 by In. So these two equations we found. So basically, the 1 by d of s is the transfer function from the noise source. So let's mark it with different colors. So if we have a noise source over here, let's call this V1. If we have a noise source over here, let's call this V2. So the noise source from V2 to the output and noise source from the V1 to the output is the same, and that is 1 by d of s. So transfer function of the noise sources are same, and that is 1 by d of s. And as far as I3 is concerned, if we do the manipulation of, so we have I3 as this equation. So if we take this equation, copy, we paste it here. So again, this can be written as so I3 can be written as I3 can be written as Q upon 1 plus SCQR into I in into 1 minus 1 by d of s. So if we do the manipulation, we get it as Q upon 1 plus SCQR into S square by omega naught square plus S by omega naught Q divided by d of s. And if we take S by omega naught Q as a common, so we get S by omega naught divided by d of s as the transfer function, and this is I3 by I in, and this is equal to V out by V3 as well. So we see the transfer function from this the noise source of this resistor to the output is a low band pass transfer function, and similarly we can find the transfer function of this node to the output, and if we do the algebra we get a similar band pass transfer function as we got in the case of I3. There will be some scaling factor difference, but it will still be a band pass transfer function. So basically, we see that the noise from the V1 and V2 are low pass in nature, while the noise from V3 and V4 are band pass in nature. So if we analyze the circuit and try to find the actual noise, we will see the noise from these two resistors will dominate as compared to the noise from these two resistors at low frequencies. So this was a low pass filter. So similarly with two op amps, we can make another filters. So let's so since we analyzed a low pass filter, we will now analyze a band pass filter. So the band pass filter case is as follows. So to make a band pass filter, this is how a band pass filter is made. So we have two op amps. V in over here, let's call this R. So, okay, let's. This is the quality factor adjusting resistor. This is R, and this goes after an inversion at the at this point. Let's call this some VL for now. This is minus VL. Now, this node over here is a band pass node. Now, if we see the previous structure and this structure, we can see a little bit of similarity and differences between that. Let's plot these two structures side by side so that we can compare them. So this is one structure, and the structure that we discussed previously, let's copy it over there. This is the second structure. So we see that the difference between these two structures is that the damping resistor is at the first integrator in one of them, and the damping resistor is at the second integrator, moved to the second integrator in the previously discussed structure. So if we analyze the transfer function from here to this node and here to this node, we get a same transfer function that can be done. And we have in your assignments, you have to analyze this structure for the output this node, which is a low pass node with a transfer function of 1 by ds, and this is also has a transfer function for of 1 by ds. However, this node's transfer function is different in this case and in this case. So you can try and analyze like what are the noise transfer function differences. So as you will solve your assignments, you can analyze you will have to analyze this structure's low pass transfer function, and you can compare the noise performance of this structure and this structure and see which one is better. So for now, for our purposes, we will solve the transfer function from input to the band pass node instead of the low pass node, that is from this node to this node. So let's resize it. So we have the band pass node over here. If we try to find the transfer function from V in to the band pass node, we get the following transfer function. So VBP. So now this point we will call as output. So V out by V in we have as S by omega naught upon S square by omega naught square plus S by omega naught cube plus 1. So you can do the math and try to find the forward transfer function. We will do the reciprocity theorem and show that we can get this same transfer function from by injecting the current here and getting the output current here in an adjoint network. So first of all, let's try to write the adjoint network of this node, this circuit. So what we will have is we will copy the circuit over here. So this node will be de-energized. This is the node where we will inject the current. Let's mark it and draw it in some different color. I in the op amps will be inverted. And same will be the case with the current source. So if we consider this as IL, so which side will this go? So earlier what we had is, if we try to increase the voltage of this node VL, the voltage of this node will decrease. The similar thing, a similar effect we need to have in the adjoint case also. So if we try to increase the voltage at this node, IL will increase and this node has to decrease. To decrease, it should take the current out of this node. So this will be equal to IL. So we have drawn the adjoint network of this. Now we will try to find the transfer function at the output and rest of the node as well. Let's call this again I3. So let the notation be same. This is I4, this is I2, and this is I3. So this is what we have now. So now this IL current over here will flow directly through this capacitor, and voltage developed at this node will be V, let's call this Vx, is equal to the impedance, that is 1 by SC into IL. Now why 1 by SC into IL? Because IL is flowing in this direction, so this voltage will be at a higher potential. So Vx is SC into IL. Let's call this one. Now this node over here is 0 volts because it's a virtual ground. So the node at so the another node, that is so the current I3 will flow as can be written as I3 equal to Vx minus 0 by R, and that is equal to Vx, that is equal to, from equation 1 we have IL upon SCR. Now the current flowing in this parallel combination of QR and C will be I3 plus I in. So let's take it to different page. Okay, we can fit something over here. So this node over here will be can be written as Vy, and Vy is equal to I3 plus I in times the impedance times this impedance. So what is this impedance? Again, this impedance is QR divided by 1 plus SCQR. And this can also be written as, if we take the QR in the denominator, so we have I3 plus IN divided by 1 by QR plus SC. So now we will see, yeah, yeah, correct. So now we will proceed further. So we'll copy this to the new page. So, sorry, we know the voltage at this node Vy, and this is equal to I3 plus In divided by 1 by QR plus SC. Now, I1 is equal to Vy by R, and same is the case with IL, and opposite is the case with I2. So we just take these two terms, and we showed previously that I3 is equal to IL divided by CR. We put it over here, and we equate these two terms. So what we get then is the following. So IL is equal to IL divided by SCR plus IN divided by 1 by QR plus SC into R. So just a minute. So it's IL by SCR, and so this current flows as so this is IL by SCR, and this is I3 plus IN. Okay, so Vy won't be, so there is a mistake of sign over here. Vy, since this current is flowing in the this direction, so this will have to be at negative potential. So Vy will have a negative sign over here, and same over here also. So this is what we have as of now. Now, if we manipulate it further, we will get IL by IN. So if we manipulate this equation, we will get the following result: S square R squared C squared plus SRC by Q plus, wait, we will do the manipulation and then come at this result. So IL is equal to minus of IL plus divided by SCR into 1 by QR plus SC, 1 by Q plus SCR. So what we have then is IL is equal to SCR by Q plus S square C squared R, and that is equal to minus of IL plus SCR times IN. So what we have then is IL by IN is equal to SCR divided by S square C squared R squared plus SC squared by Q plus 1. So if we bring the same equation from, if we bring the equation that we wrote of the forward transfer function from here, so we'll copy this side by side. So if we compare these two transfer function, we have RC is equal to 1 by omega naught. Then we get the same transfer function as the following, and hence we have proven that reciprocity is valid in this case also. So the input to output is a band pass mode. So till now we have looked at a low pass architecture with the damping resistor at the second integrator and the output at the output of the second integrator, a band pass structure where the damping resistor is at the first integrator I1 and the output is also at the output of the first integrator, that is I1. So here so these kind of structures are known as active RC structure. So there are another kind of structures that can be used to realize these filters, and those are known as GMC filter. So we will do one example of low pass filter with the GMC case also, and analyze the transfer functions. So how a GMC filter is made? So what we have over here is, now before that, let's see what GM is. What thing I'm calling as a GM. So consider this block which has some input V in, and based on the GM, that is its transconductance, it gives you the current as I is equal to GM times V in. Okay, so what we get over here now is that so this is basically a voltage controlled current source. So we can use this to make second order filters as well. So consider this structure. So how we come up with this structure, we will study later in this course. However, as of now, we can just look at the structure and analyze it. So this is a GMC low pass filter. So V in is this, V out is this, and I will write the forward transfer function directly as V out by V in is equal to 1 by S square by omega naught squared plus 1 S by omega naught Q plus 1. And in this case, omega naught is equal to Gm by C. So previously it was 1 upon RC, and in case of a trans impedance, it's Gm by C. And it makes sense dimensionally also, as Gm is basically the inverse of resistance. So dimensionally also this formula is correct. So we will try to analyze it through inter-reciprocity. Now, as we told that this GM structure over here is nothing but a voltage controlled current source whose second terminal has been grounded. So let's call this V in, and this is VO. So we have V in over here, and what we have over here is the following: Gm times V in at the output node. So this is what the structure is. Now its inter-reciprocity, how will it look? So we will look at the inter-reciprocal network as well. So how will that look? So that will look as the following. So so for a VCCS, we again have a VCCS at the in the inter-reciprocal network as well. So this will become Gm times VO, and we will give the voltage over here as VO. So you can see the skeleton of the system is still same. This is an open circuit. This is also an open circuit, and similar is are these things. And again, as far as the direction of the current is directions and the polarities of these nodes are concerned, if we try to increase this voltage, this current will increase, and this current will get pushed into this node, and it will tend to increase the voltage of this node. The similar thing will happen in this case also. If we try to increase the voltage of this node, this current will increase and push the current in V in node, and it will try to increase the voltage of this node. So with this, we can say that our inter-reciprocal network is correct. And if we look at that way, so this is nothing but an inverted GM. So here was V out, and at V internal, we have GM times V out current flowing out. So having said that, we can write the inter-reciprocal network of this transfer function, this circuit. So this will be de-energized and will be short circuited. The current will, sorry, we will, so this is I1 and this is over here is I in, and all the transconductors will get inverted. So we will have GM like this. The bubble at the output of these transconductor means that okay, wait. So we have so here this transconductor is GM by Q, and rest of the transconductors are GM. And the bubble at the output of these transconductor means that they are sinking current instead of sourcing current for a positive input voltage. So this comes in this direction, GM. This also becomes inverted, and this was GM by Q. And this is again GM. So we will apply a current I in at this direction and see what is the output current over here. So for time being, so if this current, let's say, is I1, so the voltage at this node should have been V1, sorry, I1 by GM. Okay. This is I1 by GM. Now, this I1 by GM voltage, this is V is equal to I1 by GM. And if this is I1 by GM, the current that will be flowing in this direction will be I1 by GM times GM, that is again equal to I1. So in this capacitor, the total current that is flowing is I1 plus I in. So this I1 plus I in, if flows in this capacitor, the total current, the total voltage developed at node, let's call this node Vx. So at node X, Vx will be I1 plus I in times 1 by SC. Okay. And if and the current, let's call this IY. So this current IY will be equal to minus of Vx times GM. So IY can be written as minus of I1 plus I in times GM by SC. So now we have the expression of IY. So the total current that is and if this voltage V is I1 by GM, so the current that this transistor will be sinking in will be, let's call this as IZ. So IZ will be nothing but V times GM by Q. And what is our GM? What is V? V is equal to I1 by GM. So we have IZ as I1 by Q. So a current of IZ is being pulled in this direction. So since we have already made the sign of this voltage as this current as sinking into this transconductor, so this negative sign can be dropped. So what we have now is we have a current IY that is pulled out in this direction, and a current IZ that is pulled out in this direction. So the total current that is pulled out of this capacitor is IZ plus IY. So the voltage, that is I1 by GM, can also be written as IZ plus IY times the impedance of this capacitor, that is 1 by SC. So let's write it down. I1 by GM is equal to minus of IZ plus IY divided by SC. So if we plug in the values of I1, IZ and IY, what we get over here is, we shall write it this way, I1, that is equal to minus of I1 plus I in times GM by SC plus I1 by Q. Yeah. So now what we have is, and this gets multiplied by 1 by SC. Okay. So if we solve this equation, what we have is I1 into SC by GM plus GM by S squared C squared plus 1 by SC times Q is equal to minus of I in times GM by S squared C squared. So if we take this complete term over there, what we get is we have GM over SC at this node. This seems dimensionally incorrect. Okay, so we have sorry, this term over here is so we will have GM at the top node. Okay, there is, so till this point it was correct. So we knew that I1 by GM is equal to minus of IZ plus IY by SC. So IZ plus IY is equal to SC by GM times I1. And if we put in the values of these currents, so we get minus over here I1 plus In times GM by SC is what is we have as IY, and IZ is I1 by Q is equal to minus SC by GM times I1. So if we so let's bring all the terms with I1 in one side. So we have I1 upon I1 into GM by SC plus 1 by Q plus SC by GM and minus I in times GM by SC So if we divide this complete equation if we multiply this complete equation with SC by GM, what we get here as I1 times 1 plus SC by GM times Q plus S square C squared by GM squared is equal to minus of I in. So minus 1 GM squared. So what we have over here is S. So as we mentioned initially, omega naught is equal to GM by C. If we consider that, then I1 by I in, that is equal to V naught by V in. So V naught and V in are these terms. So if we give input as V in, we get output here as V naught. So considering that, that is equal to minus of 1 upon S square by omega naught squared plus S by omega naught Q plus 1. So this is what we get, and this negative sign is because the signs of these GMs. So if we interchange this GM and this GM as this GM with a bubble and this GM without a bubble, we will get a positive sign at the output. However, here we have a negative sign at the output. So this is, but anyways, if we just look at the transfer function, we again have a low pass transfer function from input to output, a second order low pass transfer function from input to output. So till now, what all things we have seen is a low pass transfer function with two op amps. So what all circuits we analyzed till now? We analyzed second order circuits. So low pass transfer function with two op amps, a band pass transfer function with two op amps, and low pass transfer function with GMC. Now, the drawback of this GMC architecture is since the op amp based architecture, these have negative feedback. However, this is an open loop structure. So with open loop structure, the problem is that these have worse nonlinearity and noise as far as compared to their negative feedback counterparts. So now again, if we want to reduce the number of op amps in this without affecting the transfer function, so we will look at one more kind of transfer function where we can do that. So let's so what we had as a low pass filter we have discussed previously is, so we had to open, we will copy that circuit over here. So this was the first circuit, the low pass transfer function with two op amps. Let's see if we can reduce one op amp from this. So what we are going to see now is a low pass filter with second order and only one op amp. So we had this. So what we need basically are two poles. So how we can get two poles? Let's say we try to build a first order first order LPF. So in a first order LPF, we have this thing. So we have a capacitor over here, a resistor like this. This is the in. So here we get low pass that is of first order. Now, what if we just cascade one more low pass filter at the output of this first order? Here we will get a low pass transfer function that is of second order. Now, however, this is a second order transfer function. If we try to write the transfer function, what we'll get is V out. So let's call this node as V out. So V out by V in is equal to 1 upon 1 plus SCR times 1 plus SCR. Now, if you notice in this, the quality factor that maximum we can get, this node we can, let's say, call it C1 and R1. So we will have SC1 and R1. So you might have learned in the control system class that to get a quality factor greater than 0.5, the poles of the second order transfer function must be imaginary. However, in this case, you can't get by cascading these two transfer functions directly, you can't get imaginary poles, and the quality factor will always remain below 1. However, here by adjusting the value of this Q resistor, you can get any quality factor that you want. So we also know that again from the control systems basic, if we introduce some some positive feedback from this point to the negative terminal of the op amp, we can make the circuit slightly unstable, and since instability and we can push basically the poles towards j omega axis through the imaginary path. So what we'll try to do over here is, so this is a grounded node. This can be pushed to this node, but we need to invert the sign so that we can get a positive quality, positive certain amount of positive feedback. So let's see how we do that. So we had this low pass filter, first order low pass filter previously. So let's have one resistor as this resistor. Let's have as R by K, and so what we shall do is we want a positive feedback. So what we'll do is we will introduce inverter over here as -1, and this capacitor will go into this node. That let's call this C by K. Now, if we try to analyze the transfer function from V in, and this is the output node, what we get here is the following. So this is V naught. So now this is a grounded node. This is a virtual ground, so this voltage will be VG. And if we call this node as Vx, so basically this is nothing. So this complete thing is nothing but a low pass transfer function. So Vx can be written as V naught by Vx can be written as this low pass transfer function, and that is equal to 1 upon 1 plus SCR. So we have R by K and R by K and C times K, K times C. So the K in the numerator and denominator gets cancelled, and at the this is the relationship between V naught and Vx. And here we have minus Vx. So the current that is flowing through this resistor capacitor pair is now minus Vx times 1 plus SCR divided by R. So what we have now is, this is the current, and the current from here is V in by R. So the total current that flows in this direction is V in by R plus, sorry, minus Vx into 1 plus SCR divided by R. And if we substitute the value of Vx from here, what we get is, we can just write it directly as V naught into SCR whole squared. So now this current basically flows through this node, and if this is the current, so output voltage is nothing but this current multiplied by 1 upon KSC. This is the negative of the output voltage. Sorry, and this is basically minus of this current into 1 by KSC is the output voltage, as this current is flowing in this direction, so this has to be negative lower voltage. So if we write it down, if we solve this expression, we get V naught by V in as one upon S square R square C square plus SCR into 2 plus 2 minus K plus 1. Now by adjusting the value of this K, we can get higher quality factors. And mind it, this value of K cannot go beyond 2. So if we keep on increasing the value of K, what we are doing is, so if the value of K is increasing, the impedance that is seen from this node is reducing, as this is becoming R by K, the resistor is reducing and the capacitance is increasing. So the impedance seen by this node is reducing, and hence the amount of positive feedback that we are providing in the circuit is keeps on increasing. Now, after a certain value of K, what will happen is that this positive feedback will become stronger than the negative feedback that we are providing to the circuit, and the circuit will become unstable. And as far as instability is concerned, this the coefficient of this term in the second order denominator will become negative. Basically, you will be getting roots that have positive real part, and positive real part means poles at RHP. So if we increase this K moderately, we can get a transfer function quality factor anywhere from 2 to so this can give you a quality factor. If you increase it, if you have K as 0, you will get a quality factor of 2. If you keep on increasing it, you will if you have K as so the quality factor over here is, we will write the quality factor, it is 1 upon 2 minus K. So this as the value of K is equal to 0, so 0 is limiting case. So basically we have a very high input resistance. So practically no loading from this node to practically no current is flowing from this node to the virtual ground node. And this was same as the case that we discussed over here, since this current is, there is no current flowing from here to here. So it is similar to this case where your quality factor is of 0.5. And when K equal to 0, your quality factor is 0.5. If you keep on increasing K till K equal to 2, that is where when the amount of positive feedback and negative feedback almost become equal, and your quality factor becomes infinite. And this is after you increase the value of K beyond this, your circuit becomes unstable. So by moderately increasing the value of K, you can get any quality factor from 0.5 to infinity that you want from this circuit. However, one drawback of this circuit is that you are taking the output from not from the output of the op-amp, but from the output of a node which has non-zero impedance. However, the previously discussed circuit that were two op-amp based circuits, there if you see, let's say this one here, you are taking the output at the output of a op-amp. Hence, the output resistance of this circuit is zero. However, in case of the circuit that we discussed, which is also known as a reverse route structure, the output impedance is non-zero. So, and there is one more structure where this complete this thing can be shifted to uh, this point, and so you that is called a route structure. You can study it in the literature, and there, however, so I can draw the route structure for your reference. So this is basically the reverse route structure. And what is the route structure? So this is a route structure. Now the problem with this structure is that you don't get a pure virtual ground this at high frequencies when this capacitor starts becoming short, at high frequencies when this won't be a pure virtual ground. So you will have some bandpass kind of response at this node, where at low frequencies you will have actual virtual ground where this will be zero. At very high frequency, when this capacitor starts becoming short, again it will be zero, but at some intermediate frequencies that will be equal to the central frequency of the structure, that there you will have some amount of peaking in the virtual ground. So as far as the two op-amp based structure is concerned, here you have ideal virtual ground where no peaking in the virtual ground you will see. So if we compare, so this is known as a Toth-Thomas structure. So if we try to compare the routes, reverse route and Toth-Thomas, so we have route, then we have reverse route, then we have Toth-Thomas. So the output impedance is so here you are again taking the output from a low impedance node. So the output impedance is zero. Here it's not equal to zero, and here again it is zero. The virtual ground is not ideal. Here it is ideal, and here again it is not ideal. Sorry, here it is ideal, but number of op-amps, here it is 1, here it is 1, here it is 2. So if your application can handle a non-ideal virtual ground, but you need a zero output impedance, you should go with a route structure. If your impedance can handle non-ideal output impedance, however, you need an ideal virtual ground, you will go with a reverse route structure. But if you want both the output impedance as zero and an ideal virtual ground, you should go with a Toth-Thomas structure, but the number of op-amps to implement it will increase. Hence, the power consumption of this structure will increase. So This is so basically in this tutorial we analyzed some of the standard circuits used in analog IC design and tried to implement inter-reciprocity theorems on that and verify it. And in the due process, we learned about various filter architectures that are available in the literature. So this sums up the lecture for today. Thank you for watching.